Now we will generalize our basic offer-based economic dispatch formulation in three ways. We're going to include ancillary services such as reserves, we're going to include unit commitment decisions, and we're going to include transmission constraints. We'll explicitly consider reserves here in this chapter and then the other generalizations in later chapters. We'll also consider in this chapter how generally to set prices on commodities defined by system constraints and discuss the representation of those constraints. So, topics in detail: ancillary services, offer-based reserve-constrained economic dispatch, even more general formulations of economic dispatch, and corresponding to it, generalized offer-based economic dispatch. We'll look again at spinning reserve, we'll think about nonlinear system constraints, and then we'll look generally at representation of constraints. So, first, ancillary services. Because supply must meet demand continuously, our supply-demand constraint, that really is a constraint on, say, the average power production over a period of time, over a pricing interval, for example, it does not fully specify the requirements for supply-demand balance. Furthermore, because markets can't respond instantaneously to equipment failure, we need to consider recourse. We have to prepare in advance to be ready to deal with an outage if it occurs. As mentioned previously in the chapters, the additional services to fully satisfy supply-demand and satisfy other constraints, they're called ancillary services. We're first going to focus on spinning reserve. It's the capability of a generator to respond to frequency change due to supply-demand balance, and then to further respond to ISO signals to change production. As it happens, ERCOT uses the term responsive reserve to refer to both to generation that can provide such reserve and also to demand that can provide a similar response to generation providing spinning reserve. For notational simplicity, I'm going to ignore that case of demand though. And the most critical requirement for spinning reserve is the ability to increase production subsequent to the failure of a generator. We're going to focus on that issue. However, occasionally being able to decrease production, for example, subsequent to losing a large load or a sudden increase in wind generation, that might also be critical in some circumstances. And we're going to consider a so-called co-optimized market where energy and spinning reserve, and indeed other reserves, are considered together in a single market. In order to do that, as always, we need to define our variables. We must explicitly represent the power generation, and in this case, the spinning reserve of a generator. Spinning reserve is an amount of generation capacity that is kept back from using for energy. So its units are the same as units of power. Slightly abusing our earlier notation, I'm going to reinterpret the decision variable xk that's associated with generator k to be a vector. So xk now is going to be a vector consisting of pk and sk. pk is the amount of average power produced by generator k during the interval. sk is the amount of spinning reserve provided by generator k during the interval. We previously looked at and considered minimum and maximum power limits for a generator. When we're thinking about spinning reserve, there'll also be limits on the maximum spinning reserve that can be provided, and it's typically the ramp rate limits of a generator that determine that maximum spinning reserve. It's also limited by the maximum power limits, since average power production plus spinning reserve is bounded by the maximum and minimum capacity. So a typical feasible operating set for a generator that's offering spinning reserve could be something like this. Sk, it's the set of xk's in R squared. We now have two entries of xk, such that the generation pk is between upper and lower limits, such that the spinning reserve is between upper and lower limits, sk underline might be 0, and such that the sum of pk and sk is between p underline k and p overline k. So p underline, p overline k are the minimum and maximum production capacities. Similarly, s underline k and s overline k are the lower and upper limits on spinning reserve. So power needs to be within these limits, between the upper and lower power limits. Sum of power produced in spinning reserve has to be within limits. Let me call that the power plus reserve constraint. And for example, if we were also thinking about how to consider the ability to decrease production subsequent to the loss of a large load, we might use a slightly different notation or setup. So here's a picture of a typical reserve constraint. The horizontal axis on this graph is pk, the vertical axis is sk. Notice that they're different scales. Here I'm assuming that pk can generate down to 0. That's not necessarily a typical case. Maximum generation is 100 megawatts. The maximum sk that can be provided, the maximum spinning reserve, is 20 megawatts. And notice that that limits sk to be no more than 20. Similarly, pk is limited to be no more than 100, but if they're providing a non-zero value of sk, the power plus reserve constraint, which is this sloping line, limits the joint provision of power and reserve. We're going to need to think even more generally about generator constraints, so I want to rewrite it in a form that's amenable to such generalizations. So in particular, I'm going to think of sk is a set of xk's in R squared such that gamma k, a matrix that I'll define in a moment, times xk is greater than or equal to delta underline k, less than or equal to delta overline k. In this case, gamma k, which is in a set of R by 2 matrices, delta underline k is an R vector, delta overline k is an R vector where R happens to equal to 3. To represent the generator constraints I've just described, we'd have constraints that look like this. And the reason why I formulated in this form is because other generator constraints that are more complicated than I've thought of today can still be represented in this form. Sk is the set of xk's such that delta underline k is less than or equal to gamma k xk, less than or equal to delta overline k. And indeed, if the vector of decision variables for generator k is not just a 2 vector, but a 3, 4, or a 10 vector, we can represent that by a suitable matrix that has as many columns as the number of entries in xk. So, we should now consider the cost of generation to be a function of both power and spinning reserve. So in general, Fk, the cost function, operating cost function of generator k, is a function of xk, which is the vector consisting of pk and sk. Similarly, the gradient of Fk, it's the vector of partial derivatives of Fk with respect to the entries of xk, in other words, with respect to pk, with respect to sk. In principle, the partial derivatives each depend on both of pk and sk. However, it's typically the case that the cost of generation is additively separable. It really breaks up into the sum of a cost fkp for producing energy that's dependent only on pk, and a cost fks for providing spinning reserve that depends only on sk. So in that case, we can think of fk of sk to be the sum of two terms. And then in that case, the gradient breaks up into two entries, or the gradient has two entries that indeed depend only on pk, the first entry, and sk, respectively. Moreover, the reserves typically impose no direct operational cost. So in fact, typically fks is equal to 0, which means that its gradient is also equal to 0. However, we're going to see that even if the reserves cost is 0, under certain circumstances, the payment for reserves can be non-zero if certain inequality constraints involving reserves are binding. So as previously, we have a power balance constraint. We need to satisfy that, let's say, D overline is equal to the sum of the power generations. And remember, I use D overline to mean a fixed demand. We can also change that formulation to the case where we've got variable demand, and we'll do that later on. And as previously, we can write down that constraint as an equality constraint. Let me collect the entries of P, the power generations into a vector P, and the reserve provisions into a vector S. That just makes it easier to write out my constraints. Then if I write A is equal to minus 1 transpose followed by 0, then A times X adds up the entries of P minus the entries of P, and then my right-hand side equates it to minus D overline, and that gives me supply-demand balance. How about spinning reserve? So we need to think about the purpose of spinning reserve. In the case of supplying energy, it was pretty straightforward that we had a supply-demand constraint, but in the case of spinning reserve, we need to think a little bit more carefully. So I'm going to look at several formulations. We're going to focus on two of them. One that is used customarily in ISOs in North America, and another one that will lead us to some interesting insights. So formulation 1, I think of this as the most basic, to withstand an outage of the generator producing the most in the system. So in particular, for each of the generators, I'm going to require, for each generator K, I'm going to require that the sum over the generators that are not K of their spinning reserve is at least PK. At the outset, I don't necessarily know which is the largest generator in the system, nor in particular do I know which generator is producing the most in the system. That might not be the generator having the largest capacity, although generally it is. In many cases, I can guess that, though. But for now, let's not assume that we know which generator is producing the most. And so that means we're going to need to impose a constraint for each possible generator that we've got enough reserves to cover its outage. A variation on this, I'll call it formulation 2, is to withstand outages of the two generators producing the largest and second largest in the system. So in that case, I need to consider each generator, I need to consider each other generator, and now I need to sum up the reserves provided by everything but generator K and generator L, and it needs to be at least as big as PK plus PL. Each of these constraints imply a large number, each of these formulations imply a large number of constraints. We're going to consider formulation 1 in detail later. Formulation 2 is similar but has an even larger number of constraints. The two formulations, besides having a lot of constraints, also have a particular political drawback of highlighting that large generators contribute to the need for spinning reserve. And we'll see if we take it literally that these constraints imply a charge on the largest generators for their reserve implications. In other words, they're getting paid for generation, but we'll see that they need to pay for the reserve requirements they create. We'll nevertheless return to these cases when we can consider how to consider multiple system constraints. And we'll also use these two formulations to illustrate that the form of the constraint determines whether the cost of service is uplifted. Uplift means any charges other than payments for commodities. In fact, Kirschen and Stribick, in their book Power System Economics, advocate for generators to pay for reserve, and in the Australian market, frequency control ancillary services, spinning reserve in particular, for restoring frequency following a generator failure, are paid for by the generators, but not according to the pricing rules implied by the above formulations. Formulation 3 is to withstand an outage equal to some, I'll say, quotes, fixed fraction of total demand. So we pick an alpha, and we require the reserves to be at least alpha times D overline. How would alpha be determined? Well, a typical choice is the maximum generation capacity divided by D overline, although, as we'll see, that has similar implications. This formulation has the drawback of not distinguishing the effect of the maximum generation on spinning reserve. A variation on this is to procure the spinning reserve in every hour to withstand an outage equal to some fixed fraction of the demand that occurs in the hour of the peak. The last formulation, and the one that we're going to focus on for a while, is to withstand an outage equal to a fixed requirement. Sum of the reserves is greater than F overline, where F overline is, again I'll use quotes, some fixed amount of required spinning reserve. So we'll first literally think of F overline as constant, but then we'll consider the implications of it actually depending on system conditions. Whichever formulation we choose, we can write the spinning reserve constraint in the form Cx less than or equal to D. So for example, for the fixed requirement formulation, we could write C is equal to zeros, followed by minus ones, and D is equal to minus F overline. It's kind of similar to the supply-demand constraint, but now it's related to reserve, spinning reserve, and it's an inequality constraint. So we're going to consider this formulation in detail, and then we'll consider some of the other formulations. So reserve constraint economic dispatch says, let's find the generation that minimizes the cost subject to the constraints. Let's, as I mentioned, assume a fixed spinning reserve requirement. The definition of X, my decision variable, is the set of generations, the collection of generations, I should say, followed by the collection of spinning reserve assignments. We've seen A and C. Let me define AK to be the columns of A associated with the variables PK and SK that represent generator K. AK, in other words, is minus 1 and 0, because the column of A associated with PK is a minus 1 entry, the column of A associated with SK is a 0 entry. And similarly, let's define CK to be the columns of C associated with the variables PK and SK. So in this case, CK is 0 and minus 1. In fact, A and C are exactly one row each, so columns are kind of boring. They only have one entry. When we generalize to the case of more than one system equality constraint and more than one system inequality constraint, these matrices, AK and CK, they'll consist of columns with more than one entry and multiple columns. They'll have columns that are actually vectors. So let's suppose we find a minimizer X star of the reserve constraint economic dispatch problem. This problem is convex, so the first order necessary conditions are also sufficient. So we can write down the first order necessary conditions. We've seen this general type of situation before. We've got the first set of lines of the first order necessary conditions. Remember, they always have terms with the gradient of F. There's a term involving the equality constraint matrix multiplied in the Lagrange multiplier, then terms involving the inequality constraint matrices. The inequality constraint matrices include the system constraints, CK, but also the generator constraint matrices, gamma K. And gamma K is repeated because we had double-sided inequalities. We have complementary slackness on the system inequality constraints. We have complementary slackness on the generator constraints. We have our inequality constraints, equality constraints, inequality constraints on system constraints, generator inequality constraints, and of course non-negativity on the Lagrange multipliers. Mu star is the Lagrange multiplier on vector of Lagrange multipliers on the system constraints. Mu underline K star, mu overline K star are the vectors of Lagrange multipliers on the generator constraints. And as usual, capital mu is diagonal matrix. If we plug in the specific entries from A and C, what we find is that the terms CK and AK, because of their special structure, give us this. Remember, gradient FK is a 2-vector. Even though it's separable, it's a 2-vector, and we get a slightly simplified version as shown here. So previously we had the mu's having a role as Lagrange multipliers, the mu underline and overline, Lagrange multipliers on the generator capacity constraints. Now they're different, they're expanded compared to the previous cases, but they're still Lagrange multipliers. And similarly these, and they're Lagrange multipliers in particularly on the generator constraints. In particular, mu underline KL, mu overline KL star are the Lagrange multipliers on the constraints gamma KL x K star is greater than or equal to gamma underline KL, and similarly for the less than or equal to constraint, where gamma KL is the lth row of K. So gamma K is a matrix associated with generator K, its lth row is gamma KL. And similarly, KL on the deltas indicate the lth entries. Lambda star, mu star are Lagrange multipliers on the system constraints. We will distinguish system constraints and their Lagrange multipliers from generator constraints. Let's see an example to make this a bit more concrete. Example 5.6 from Kirschen and Strubik. It's got 4 generators. Minimum production and minimum reserves is 0. The other capacities and the marginal costs are as shown here on this page. We've got several large generators, 250, 230, 240, 250 megawatts of capacity, 2 generators that can't provide any spinning reserve, and 2 other generators that can. The marginal cost of energy production, this generator is cheap, $2. The first generator is cheap, then somewhat rather more expensive for generator 2, $17. Even more expensive, $20. Even more expensive again, $28. The direct reserve marginal costs are 0. Spinning reserve costs are 0. We're now going to consider 2 demand levels. D overline is 300, D overline is 500 megawatts. And we're going to require required spinning reserve to be at least a specific requirement of 250 megawatts. So, before we specialize to the particular cases of the demand of 200, 300, and 500, let's look a little bit at the problem to get some insights that will enable us to solve it without explicitly using software to solve it. Generator 1 can't provide spinning reserve. It's got the lowest marginal cost, so pretty obviously we would like to use it to make energy. And in particular, for any demand equal to or above 250 megawatts, generator 1 is going to be fully dispatched. The optimal values of power and spinning reserve for generator 1 are going to be, in this case, 250 megawatts of production, 0 megawatts of spinning reserve. Only generators 2 and 3 can provide spinning reserve. Neither can provide all of the spinning reserve, the required spinning reserve of 250 megawatts. So they're both going to have to provide spinning reserves. Generator 2 has the lower marginal cost amongst generators 2 and 3. So what we're going to want to do is use generator 2 to produce as much energy as possible, consistent with meeting the reserve constraint. And we're going to use generator 3 to provide as much spinning reserve as possible. So that means that the optimal value of spinning reserve from generator 3 is going to be as much as possible. S3 overline is 190 megawatts. The optimal spinning reserve from generator 2 is going to be whatever we need to make up the rest of the spinning reserve. That will be F overline minus S3 star, 250 minus 190, or 60 megawatts. Let me call that a tentative solution because we need to make sure it satisfies all of our requirements, but so far that looks to be the right direction. Let's specialize and make sure everything else works. D overline is 300 megawatts. For D overline equal 300 megawatts. The other optimal values are going to be whatever is needed to generate a total of 300 megawatts. So if we've got 250 from generator 1, then the rest is going to come from the lowest cost of the remaining generators, generator 2, which will provide the other 50 megawatts. Generator 3 and 4 will produce 0 megawatts, and generator 4 will contribute 0 megawatts of spinning reserve. Notice that the upper limit on the 3 generator constraints for generator 1 are binding. None of the 3 sets of generator constraints for generator 2 are binding, and only the upper limit on the spinning reserve constraint for generator 3 is binding. This is our solution. And it satisfies that the reserve is 250 megawatts and we have met demand with supply from generator 1 and generator 2. So let's see if we can extract the Lagrange multipliers. The first line of the first order necessary conditions for generator 2 says this: since the mu underline and mu overline are 0, we're left with gradient of F2, which is $17 and $0, minus lambda star mu star is equal to 0. That tells us that lambda star is equal to $17, mu star is equal to $0. That tells us that increasing demand would require, since it would require increasing generator 2 production, that would cost $17 per megawatt per hour for each for additional demand. $17 per megawatt hour for additional megawatts of demand above 300 megawatts. Furthermore, increasing spinning reserve requirements would require additional spinning reserve for generator 2, but that would not cost us any additional. So lambda star, mu star give us the sensitivity of surplus to changes in demand and spinning reserve respectively, recalling the sensitivity analysis results. Now let's turn to D overline equal 500 megawatts. The other optimal values are going to be P2 star is equal to P2 overline minus S2 star. That's 230 minus 60, or 170 megawatts. P3 star is 50 megawatts. That adds up to 250 from generator 1, 170 from generator 2, 50 from generator 3. We need another 30 megawatts, and that's going to come from generator 4. So the upper limit on the 3 generator constraints for generator 1 is binding. Only the upper limit on the power plus reserve constraint for generator 2 is binding, and only the upper limit on the spinning reserve constraint and the power plus reserve constraint for generator 3 is binding, and only the spinning reserve constraint for generator 4 is binding. Let's see if we can figure out the Lagrange multipliers. The first line of the first order necessary conditions, again for generator 4, gives us this condition. In this case, we've got a couple of particular constraints that are binding. In particular, the middle constraint on reserve lower limit is binding, although we'll see that it's only just binding, and the corresponding upper limit is also just binding, and again we'll see it's only just binding. Focusing on the first line of the condition, however, notice that it doesn't have any of the mu's in it. So that means that $28 minus lambda star is equal to 0. That's the same as we saw before for the 300 megawatt case. It just happens to be the same. It's different to the previous case. We find that now lambda star is $28 a megawatt hour. That's different to the case with 300 megawatts of demand. So for 500 megawatts of demand, the first line of the first order necessary conditions for generator 4 tells us that now the energy price is going to be, well, the Lagrange multiplier on energy is $28 per megawatt hour. For generator 2, we get a slightly different set of conditions. And these conditions both involve mu overline 2, 3. And the reason for that is that none of the lower bound constraints for generator 2 are binding. Only the upper bound constraint on the power plus reserve for generator 2 is binding. So plugging in, multiplying these matrices into mu2 underline, mu2 overline, what we find is that we get an entry here and here that's both equal to mu2 3 overline star. Notice that that's going to tell us something about mu2 3 overline and about mu star. Focusing on the first line of the condition, we get that 0 is $17 per megawatt hour minus lambda star plus mu2 3 overline. So now we can rearrange that to evaluate mu2 3 overline star. It's $11 a megawatt hour. Focusing on the second line of the condition, we get this. So this tells us that mu star is equal to mu2 3 overline star. In other words, mu star is equal to $11 a megawatt hour. So again, using our sensitivity analysis, increasing demand would require increasing generator 4 production. That's different to the previous 300 megawatt demand case. In this 500 megawatt demand case, we're dispatching generator 4, and it is marginal. Increasing demand would require increasing generator 4 production, which would cost $28 a megawatt hour. For the case of reserves, though, there's a rather more subtle story. Increasing reserve requirements would require additional spinning reserve from generator 2, but generator 2 was the cheapest generator amongst 2, 3, and 4. Remember, generator 1 was fully dispatched and wasn't providing any reserves. So if we need more reserve from generator 2, we're going to be able to produce less energy, less power from it. What does that mean? We're going to have to generate more power from generator 4. And on net, each extra megawatt of reserve would force us to increase generator 4 by a megawatt, which would cost an additional $28 a megawatt hour. Of course, we'd be generating one less megawatt from generator 2. However, the net effect would be increased by 28, savings of 17, a net cost of $11 a megawatt hour. So what we can see is that there's a non-zero Lagrange multiplier on spinning reserve, even though the direct cost of supplying spinning reserve is 0. So let's now translate that into offer-based reserve constraint economic dispatch. If we want to implement the results of economic dispatch, the ISO has to ask each generator K to produce at a level XK. Remember, that involves a generation, PK star, a reserve, spinning reserve commitment, SK star, that results from the reserve constraint economic dispatch. We're going to define a pricing rule that aligns the private incentives with the public goal of economic dispatch. Previously, for energy, we proposed a pricing rule, and we then verified that it aligned private profit maximization by each generator with achieving economic dispatch. We're going to see how to do this generally, to align incentives when there are multiple commodities. In this case, we've got energy, power, and reserve as our two commodities. So let's consider generator K, and let's suppose that it's paid some price pi sub P for its power production, and some price pi sub S for its reserve contribution. The revenue to generator K then would be pi sub P times Pk plus pi sub S times Sk. So if we arrange the prices together into a vector, pi P, pi S, then we could express the revenue as that vector of prices transposed times Xk. We're going to continue to assume that generator K cannot directly affect the prices, and furthermore that it desires to maximize its profit. Equivalently, generator K wants to minimize the difference between its costs and its revenues. The problem faced by the generator then would be minimize cost minus revenues. I've shown that at the bottom of the page. What are the first order necessary conditions for that? Well, as before, I need to distinguish the ISO dispatch from what the profit maximizing solution for a generator would be. So let me write double stars for the profit maximizing condition. I can write the first order necessary conditions down. They're shown here on this page, and they just simply derive from the basic profit maximization problem. As previously, when we were just considering generation, remember that generator K enforces its own generator constraints. It's not going to generate it lower than its production minimum, and it's not going to be able to generate it higher than its production maximum. So it will indeed find a solution, XK double star, together with Lagrange multipliers, that satisfy these first order necessary conditions. First lines involve the gradient. The next two are complementary slackness. The next two are generator constraints. The last are non-negativity on Lagrange multipliers. So how would we make the solution of those first order necessary conditions for maximizing generator K's profit consistent with the results of economic dispatch? Well, we'll just compare corresponding lines in the two sets of first order necessary conditions. Here is the first order necessary conditions for profit maximization. Here are the first order necessary conditions from the ISO problem. What you can see is that they look very similar. Double stars, of course, in the first lines, single stars in the second, but notice that we've got gradient FK. We've got gamma K multiplied into a Lagrange multiplier, gamma K multiplied into a Lagrange multiplier. Similarly, the thing that needs to be aligned is the vector of prices in the first equation and the corresponding terms in the second equation. All we're going to do is define prices pi sub p and pi sub s so that xk double star would be a solution to the second set of equations. By the way, if fk is not strictly convex, then as usual there might be other solutions. Well, comparing the first lines, it's pretty clear that what we need to do is set the vector of prices to be equal to minus ak transpose lambda star minus ck transpose mu star. And that translates to lambda star mu star. This probably shouldn't come as a surprise. We're going to pay for energy based on lambda star, the Lagrange multiplier on power balance. We're going to pay for reserves based on the Lagrange multiplier on reserve constraint. So generalizing the energy only case, if the ISO sets prices on power and reserves equal to lambda star mu star, then the single star solutions, the solutions from the ISO problems, are also will satisfy the first order necessary conditions for profit maximization. If fk is strictly convex, then they're the only solution. So xk double star equal to xk star, the ISO solution, and similarly for the Lagrange multipliers, are the unique profit maximizing solutions. The market clearing prices in this case strictly support economic dispatch. If fk is convex but not strictly convex, then there can be multiple maximizers. But the choice xk star is consistent with individual profit maximization. We could say that the prices non-strictly support economic dispatch. The ISO will have to tell the generator that it wants it to dispatch at xk star, but that's fine because that's consistent with profit maximization. Let me observe that if the spinning reserve offer price is 0, then fk is convex but not strictly convex. The price for energy, we typically write the units for that price as dollars per megawatt hour, but since spinning reserve is typically procured on an hourly basis, we will write units for the price of spinning reserve as dollars per megawatt per hour. They're the same, but I've written them slightly differently. A couple of observations. The spinning reserve price in a co-optimized energy and reserves market can be strictly positive even with zero offer prices. A generator providing spinning reserve is paid a non-zero price for providing capacity for spinning reserve that reflects what is known as the opportunity cost. In this case, the opportunity cost of the foregone profit that it didn't earn because it didn't use the capacity to make energy. Instead of making energy and selling it at the energy price, of course costing it its fuel cost, its marginal cost, instead of doing that, it reserved its capacity for spinning reserve. The generator is paid the opportunity cost of the foregone profit. And that opportunity cost equals the difference between the energy price and the energy offer of the generator. For low levels of required spinning reserve, or if there is a lot of available capacity, the spinning reserve price may end up being 0 or low. That occurred for demand equal 300 megawatts. For high levels of required spinning reserve, or if the supply is tight, the spinning reserve price may be high because of the opportunity costs. And so this will be a similar case will apply for all types of reserves. Here's a qualitative illustration for spinning reserve. My spinning reserve requirement in megawatts is on the horizontal axis. The price of the spinning reserve in dollars per megawatt per hour is shown on the vertical axis. The solid curve shows the case when we've got significant available capacity. The spinning reserve price might be 0 all the way out to quite a significant level of spinning reserves, then increases. On the other hand, the dashed curve shows the case when we have a tight capacity constraint. Spinning reserve price might still be 0 or close to 0, but then it will start increasing, and it will in general be higher than the price of spinning reserve when there was significant available capacity. We've continued to assume that offers were based on marginal costs. Let's revisit that in the particular case for reserves. In the discussion of offers for power and energy, there were clear downsides to misspecifying a marginal cost or even a capacity, given the price-taking assumption. If you specified an offer for energy to be different to marginal costs, that reduced profits. Specifying the capacity to be less than the actual capacity reduced profits. Specifying the capacity to be greater than the actual capacity in a forward market involved a speculative offer, which was risky. And specifying the capacity to be greater in a real-time market would result in deviation penalties. Given the price-taking assumption, specifying the energy or spinning reserve offer to be different to the corresponding marginal cost, or specifying the capacity to be less than the actual capacity, will still result in profit reduction. But how about the upper limit on spinning reserve? If you specify it to be greater than the actual upper limit on spinning reserve, what happens? Well, unless the capacity is actually called on, there is nothing actually done in providing spinning reserve. And that is only going to be called on occasionally. The implication is that non-compliance penalties or operational tests are going to be necessary to ensure that reserves capacity is not exaggerated. Typically, most ISOs have some sort of operational tests to check this out. Let's see an example of offer-based reserve-constrained economic dispatch. We'll use the same example as before, so we're going to be very easily able to write down the prices. We'll assume that the offers reflect marginal costs and actual capacities. The price-taking assumption, together with additional assumption that offered spinning capacity equals the actual spinning reserve capacity, will guarantee that the generators will, in working in their own interests, make offers that reflect marginal costs. So for both demand levels, generator 1 is going to be fully dispatched. It produces 250 megawatts of power, spinning reserve 0 megawatts. Now specializing to 300 megawatts of demand, we've seen the dispatch conditions before. P1 is 250 megawatts, P2 is 50 megawatts, it provides 60 megawatts of reserve, P3 is 0, S3 is 190, generator 4 doesn't do anything. The energy price is $17 a megawatt hour. If demand increased, generator 2, which is marginal, would produce additional power. The capacity constraint of generator 2 is not binding, mu star is 0, so the spinning reserve price is 0, and indeed, if we needed additional spinning reserve, then there would be no additional dispatch cost. Notice that we've assumed the reserve offers were at $0. If the reserve offer prices were non-zero, then the prices for reserves would be non-zero even in this case. Now turning to 500 megawatts. We've seen the generation before. Generator 1 is fully dispatched to provide power. Generator 2 provides 170 megawatts of power, 60 megawatts of reserves. Generator 3 provides 50 megawatts of power, 190 megawatts of reserve. The sum of the two reserves from the generators adds up to 250 megawatts. Generator 4 provides 30 megawatts. Generator 4 is not fully dispatched. It's got marginal cost of $28 a megawatt hour, and indeed that's the energy price. That reflects the fact that to meet an additional megawatt of demand, we'd use generator 4 that had an offer price of $28 per megawatt hour. On the other hand, the capacity constraints of generator 2 and 3 are binding, and mu star is $11 a megawatt hour. The spinning reserve price is $11 a megawatt hour. That reflects the difference in the offer prices of generator 4 and 2 for energy. The spinning reserve price, we can also think of it as equal to the opportunity cost for generator 2 to not sell more energy at the price $28 per megawatt hour. Notice that the power plus reserve constraint of generator 2 is fully dispatched. It's equal to its capacity. Generator 2 is actually indifferent to the sharing of its capacity between power and spinning reserve. Because either it would generate, costing $17 a megawatt hour given its marginal cost, it would be paid $28 a megawatt hour, therefore receiving an operating profit of $11 per megawatt hour. Or it could provide spinning reserve, doesn't cost it anything, it's paid $11 per megawatt per hour, and therefore also receives an operating profit of $11 per megawatt per hour. The power plus reserve of generator 3 is also a capacity. However, its reserve constraint is binding. Generator 3 would prefer to provide even more spinning reserve if it had more spinning reserve capacity. Why is that? Well, its marginal cost is 20 and it's paid 28. So it receives an operating profit for energy of 8, but if it could provide more reserve, it would receive an operating profit of 11. So generator 3 would prefer to provide more spinning reserve, but it can't because it's at its capacity. The price for spinning reserve is non-zero for D overline is 500 megawatts, even though the offers for spinning reserve are zero. This is a very important point. Of course, if the offers were non-zero, we would have non-zero prices. However, the key point here is that the prices are non-zero even though the offers were at zero price. As I mentioned above, the price for spinning reserve represents the opportunity cost to generator 2 of foregoing the inframarginal rent. This opportunity cost is automatically represented in the price for spinning reserve because they're considered together. Energy and reserves are considered together in a co-optimized formulation as in the day-ahead ERCOT market. In contrast, in the previous ERCOT zonal market, there was a day-ahead market for ancillary services, including reserves, but there was no associated day-ahead market. The market for reserves in the day-ahead AS market in the previous zonal market and the market for energy in the balancing market was separated. In the separated AS market, prices for ancillary services, including spinning reserve, could only be non-zero if the offers were non-zero. Certainly, a profit-maximizing generator would not give away its capacity for zero, which it would otherwise, that is, it would not willingly forego the operating profit from selling energy into the balancing market. That means that offers into the previous ancillary services market were made at an offer price that reflected the expectation of the offer price, of the operating profit, that would have been received for selling energy in the balancing market. In other words, offers would reflect an estimate of the difference between the energy price and marginal cost. Since forecasting the balancing market energy prices is pretty hard, it was difficult for market participants to find an appropriate offer price. How about prices for demand? When we discussed the pricing rule for energy, we observed that the demand would pay for energy at a price equal to the Lagrange multiplier on the power balance constraint. So demand consumed D overline, it would pay a total of lambda star times D overline. The total power generation was D overline. The generators were paid a total of exactly the same, lambda star times D overline for their production. In other words, for energy, the payment from the demand for energy equals to the payment to the generators for energy. How about spinning reserve? Well, the total provision of spinning reserve by the generators was F overline equal to the sum of the reserves. They would be paid a total of mu star times F overline. Where's that money going to come from? We need to pay them. Unfortunately, there was no explicit dependence of the spinning reserve requirement on the demand D overline in the fixed formulation of spinning reserve. F overline is apparently fixed. So in that formulation, we're going to need to uplift, that is to say, charge the spinning reserve payment of mu star times F overline to demand. A typical situation, but there are variations on this, the payment could be charged to the demand by adding a pro rata share of the spinning reserve cost to the energy price paid by the demand. That would effectively increase the price of energy by the amount needed to cover the spinning reserve. In this case, mu star times F overline divided by D overline, so that then the payment by the demand for spinning reserve would match the payment to the generators. Let's try and interpret that a little bit differently. Let's suppose the demand is bid with a willingness to pay. So now D is a scalar representing the consumed power, and we include the constraint 0 is less than D overline, and a term F naught that represents minus the benefits. we're going to change gears a little bit and consider the formulation of spinning reserve, where the spinning reserve needed to cover a fixed fraction of the demand. F is equal to alpha D. So in this case, in this formulation, the demand will appear twice in the system constraints. First, power balance. Second, spinning reserve requirements. And notice that in this formulation, there's an explicit dependence not only of power on demand, but also of reserve on demand. And this will change the interpretation of the spinning reserve payment. To represent demand into the reserve constraint economic dispatch, we need to add columns A0 and C0 that represent demand, and they are of the form 1 and alpha. If we look at the first order necessary conditions for economic dispatch, we see in the dispatch including demand a term like this. As it happens, this is also one line of the first order necessary conditions for this problem, which is precisely the problem of minimizing the payment minus the benefit. In other words, maximizing benefit minus payment by demand. So paralleling the previous discussion, the price to align the demand, to induce it to have behavior consistent with economic dispatch, would be this coefficient here of D. In other words, they need to be charged lambda star plus alpha mu star. This is the sum of a marginal energy cost plus a share of the marginal reserve cost. So for example, if we fully dispatch the demand, if D star is equal to D overline, then the demand consumes D overline of power, and it will pay lambda star plus alpha mu star times D overline, which is equal to lambda star D overline plus mu star alpha D overline. Well, that's good, because that means the total payment is going to equal the payment for energy to the generators and the total spinning reserve payment. Because remember, alpha D overline equaled the total spinning reserve. So in this case, the payment from demand equals the payment to generators, and there is no uplift. So the conclusion here is if reserves or any other ancillary services are explicitly represented as proportional to demand consumption, then there is no uplift, since the total payment by demand equals the total payment to generators. Demand would be charged based on the marginal cost of service. That share alpha is based on the reserve requirement as a fraction of demand. If alpha is chosen to be F overline divided by D overline, then the total payment by demand for energy and spinning reserve for the fixed fraction formulation is going to be the same as the pro rata uplift, in the fixed requirement formulation. So the payment under pro rata uplift provides the right incentives to demand if the required spinning reserve was actually proportional to demand. Unfortunately, this is not a correct model of the need for spinning reserve. So that means that pro rata sharing of spinning reserve procurement costs, as practiced in ERCOT and other North American markets, doesn't actually provide efficient incentives for consumption. Having said that, distortion of consumption decisions are likely to be small because the overall cost of spinning reserve is small compared to the average energy cost. Just one final comment. Note that in the context of a day-ahead market, the spinning reserve constraint might be based on the peak demand over the day. In that case, the price should be, in principle, associated with the peak demand in that particular hour. No.